up on the counters that are vicious combined and not big enough, those are oftentimes infrared lights. You know that to be warm until the fish picks it up. Okay, now this has to do with ionizing radiation. And I just want to give you, please do not memorize. It's not meant to be memorized. But I want to show you the variety of different tolerances that microorganisms exhibit to gamma radiation, ionizing radiation. Don't worry about the term they use, just look at the values here. I can tell you that the typical exposures for lethal exposure per unit is about 5 grays. 5 grays. And these are kilograys. And these are thousands of grays. E. coli, one of the weakest tolerated ones, 1.8, 1,800 grays can tolerate that. But we're typically be subjected to a higher concentration and we can kill them. So look at our Mycobacterium tuberculosis, very low number, very low number. Viruses are typically larger. There's a variety of different reasons for that. Yeah, it says it's rats. Stuff like that, yeah. Again, the rats are very comparable to a gray. In fact, I'm trying to change this one. I didn't get your choice. Just look at the values. Just look at the values. Okay? All right. Now, we talked about the fact that ultraviolet light is not as penetrating and is not as energetic. Therefore, its usefulness is much more limited. It's also limited by the fact that many microorganisms have evolved mechanisms to repair that damage. They can repair damage induced by ultraviolet light. DNA absorbs maximally around 260. And it is the pyrimidine bases within the DNA that absorb the most of that radiation. Not the purine, the pyrimidine. Such that when we have two pyrimidines adjacent on the same strand, that energy is sufficient to break the hydrogen bonding with the purine across the strand, and it produces what is referred to as pyrimidine dimers or cyclobutane dimers. Cyclobutane dimers. This causes a problem when the cell is replicating or if it's undergoing transcription, because when those enzymes reach this point, they go, oh, what's the one? It's like a giant pothole in the river. A big old sinkhole, 6 feet deep, 6 feet deep. You can't go anywhere. So what they do, these organisms have evolved means to fix it, repair it. It's called photoreactivation. It's one of the first ones that was described. It's part of the SOS repair mechanism. If you do anything in genetics, you'll read up SOS repair mechanism. It involves an enzyme that scans the DNA. Our DNA is constantly being scanned. It's constantly being scanned for errors and picked up. We have what are called error-prone enzymes that detects them and fixes them. Well, this particular one is activated by light. I don't know, I'm getting ready to stop. It's activated by light, and we call it photoreactivation. But what it does is it scans the DNA, locates it. There is an enzyme that takes some of that energy, that has enough energy to break that double bond and reestablish those pairs. This limits the usefulness of UV light. This makes the ability of UV light to control organisms very, very minimal because they all have these repair mechanisms. Okay, yes.